Welcome, everyone. Welcome to the Mid-Atlantic Micro-Nano Alliance virtual seminar series. Today we have a very special guest. We have Dr. Kevin M. Daniels, who is an assistant professor in the Department of Electrical and Computer Engineering with a joint appointment at the Institute for Research in Electronics and Applied Physics. Born and raised in Columbia, South Carolina, Dr. Daniels received his BS, ME, and Ph.D. in electrical engineering from University of South Carolina in 2009, 2012, and 2014, respectively. From 2014 to his start at UMD in 2017, Dr. Daniels served as a National Research Council Postdoctoral Fellow, residing at the U.S. Naval Research Laboratory in Washington, D.C. So, Dr. Daniels, let's hear what you have for us today.
Well, first, I'd like to thank you, Heidi and Ryan, for setting up the space to keep the science conversations going in this virtual venue. And channeling my inner PBS, definitely watching more than my fair share of kids shows on PBS with the pandemic, thanks to viewers like you. So today my talk is basically about the material that really enables all the work that goes on in my lab. So, we're going to focus on graphene and basically using it as a scaffold to build, all these different electronics and sensors. So just kind of, let you can see in the background of this title slide, graphene is a single atom thick two-dimensional layer of carbon atoms with some pretty amazing electrical, optical, and structural properties. And in my lab, we use this graphene as a scaffold to make what's called two-dimensional heterostructures. So we're putting two-dimensional materials that are different from graphene in both composition and properties on top to change some of these properties for different applications. So none of this work would be possible without the fantastic researchers in my lab, including my postdoc and 3 graduate students and a host of undergraduates as well. We're on the wonderful University of Maryland College Park campus. Here is a group photo after a very delicious pizza party that we had last summer. We're housed in the Institute for Research in Electronics and Applied Physics building. And in here is really the piece of equipment that sort of takes up a large space of my lab. This is a chemical vapor deposition chamber used for synthesizing a lot of these two-dimensional materials. So before we get into two-dimensional materials, I really want to kind of cover why, these materials or these solid-state electronic materials important. And it goes beyond, just talking about the transistors that we typically think of when we think of electronics, but it also goes into lighting and medical devices, harvesting energy, all the way into electric vehicles, power electronics, batteries, computing, definitely, with video games and such, as well as when we think of sort of next generation materials. So we're talking about flexible materials that have, a lot of these additional properties. Now, for the most part, when it comes to introducing new materials into this space, whether it be, conductive, insulating, or semiconducting, really it has to do one thing, and that's beat silicon. It's really difficult to beat the cost of sand. And so really you have to either one, have properties that beat silicon, by some leaps and bounds, such as, with light emitting diodes, silicon makes a terrible light emitting diode, or you do something that silicon can't do, such as, become part of flexible electronics. Kind of give you a case study. If you look at solar cells, silicon is an okay material for solar cell. It's definitely not the best, but just from a cost perspective, it really, gets the job done and really is difficult for additional material to actually kind of take that place, unless you can beat it in terms of cost. In my lab, we really are focusing on applications that really silicon can't do. So we focus on, the physics that we can get from these two-dimensional materials. So reducing the dimensionality, you gain an entirely new regime of different physical phenomenon, and really the material kind of shines as a result. So again, in my lab, we focus on what these materials are called van der Waals materials. These materials are layered materials that are sort of held together by this very weak van der Waals force. And as you can see here at the bottom here, we have this heterostructure that we make in the lab. We take bulk 6H silicon carbide. From there, we synthesize this two-dimensional layer of graphene that I showed on the first slide. And then from there, we're able to synthesize this delta phase manganese dioxide, which is a transition metal oxide that has some pretty interesting properties for sensors. And so, as shown here, we really focus on, again, things that silicon has a difficult time with, such as, making very sensitive and selective sensors, electrodes for energy. So you can see fuel cells, batteries, and capacitors here. Definitely in the optical regime, so graphene-based plasmonics, so operating in really the underdeveloped terahertz regime. Materials and devices for things like communication, and for optical, definitely a lot of different optical properties, like identification of let's say cancerous cells. That's where terahertz really shines. And of course, and I'll show later wise, graphene is actually a really good material for electron emission, and you can actually get field emission of X-rays as a result. And so we work on all of these applications, including ferromagnetic materials as well, but we work on all of these applications because the materials really allow us to be able to create these sort of devices for these applications. And my lab is mainly focused on the synthesis of these materials and then fabrication of these devices. And so here we have, again, this chemical vapor deposition system for fabricating some of our materials. And then down here is what's called an electrochemical cell, where we can place our graphene here. We have electrolyte solution, and we're actually able to build materials by applying a potential in that manner. And this is how we actually synthesize this delta phase manganese dioxide for sensing. Now, manganese dioxide is a very interesting material, like I said, for sensing, but it also is actually a very useful material for batteries because I know a lot of you have heard of lithium-ion batteries, but the interlayer spacing between these materials, or this van der Waals, force that's causing the materials to separate, actually allows for ions bigger than lithium to actually fit in, like sodium and magnesium, for instance. So again, the focus of the lab is really material synthesis of these two-dimensional materials. And so this is sort of an overview of the lab, of the talk today. So really looking at two-dimensional materials and applications, how we synthesize them, this van der Waals epitaxy, so basically being able to grow things on graphene without having to lattice match. If a material has, and I'll show later, if a material has a different lattice than the material you're trying to grow on, you can actually encounter a lot of really nasty effects that causes defects due to strain. And so using graphene, you can kind of get around that. And then lastly, we'll talk about the fabrication and testing of these heterostructures. And we're actually able to fabricate these gas sensors with really unprecedented properties. So the first material for that was, or the first two-dimensional material rather, is graphene. So the single layer of carbon atoms, only an atom thick, 1.7 angstrom, so very, very thin material with some exceptional properties, including the high electrical conductivity, high room temperature mobility. So if we apply a volt to this material, our electron will move 100,000 centimeters in the material if we apply a volt here in 1 second. So these electrons are booking it, and they're able to book it through the material due to this quasi-ballistic transport. And so the electrons are actually able to move without mass in the material. So it's very, very fast. High surface area, so every single atom on the surface is basically exposed to an environment. So it actually makes it an excellent material for sensing. And then relatively low noise. So if we make a device out of this material, we really don't have to amplify it. Well, if we do amplify it, we won't get killed with this noise background. And like I said, this graphene really can be seen as just two-dimensional material, but really it's just from bulk graphite, right? In fact, the first isolated graphene was basically done by Scotch tape by Andrei Geim and Konstantin Novoselov, who exfoliated by basically taking Scotch tape to the material, and they were able to isolate a single layer. Now, this existence is really actually counter to theory, basically saying that, hey, if you heat up this material, the lattice vibration would rip this material apart if it's two-dimensional. There's nothing to support it. But graphene is great because the carbon-to-carbon bonds here are actually 4 times stronger than steel. So it's actually able to withstand that vibration of the atoms, at room temperature. So as I said, graphene is held together by these van der Waals forces. So just like with your pencil lead, if you write on the paper, the graphite will leave your pencil and go to the paper. So this is very, very weak force that's kind of holding these layers together in the material. Now for sensing, again, this material is very sensitive with all the atoms exposed to the surface. So if an atom lands on it here, or a molecule, excuse me, then it actually interacts with these pi orbitals here, which is how graphene gets its ballistic transport of carriers. So electrons are essentially hopping here, and as shown here, our energy will actually go up, and we're actually either giving electrons, or we're taking electrons from the material and actually changing the resistance of the material with the molecules, but the material still remains pretty conductive as a result. Also, just kind of a side note, the Andrei Geim, who won the Nobel for graphene, for his work in graphene in 2010, also won the Ig Nobel a few years earlier by magnetically levitating a frog. So he's one of the only people to have won both awards. So again, weakly attached molecules act as donors and receptors, very weak van der Waals force, and we have changes in carrier concentration, but the material still remains really conductive. And this actually is a problem for sensors because since all atoms are exposed and is actually pretty receptive to this electron transfer, because again this is where your charges are moving in your material, it actually makes for a very sensitive material, but not a very selective material. And so this is an issue that we're trying to address with sensors by making heterostructures out of them, out of other two-dimensional materials. So is there a way to improve the selectivity for sensing? Now, since this discovery in 2004, there's been a host of other two-dimensional materials that have been discovered, ranging the gamut from being, the semi-metal material in graphene all the way to semi-insulating in hexagonal boron nitride. And then there's been a lot of work in this semiconducting transition metal dichalcogenides like molybdenum disulfide. And one of the materials that I'm really interested in, especially for sensing, is this transition metal oxides, like manganese dioxide here, mainly because it has very unique charge transfer capabilities, and people have actually made particles of this manganese dioxide and actually have introduced them into battery electrodes and have improved things like current density by a large amount because of this unique charge transfer capabilities. And two-dimensional materials can be seen essentially across the entire spectrum, going from semi-metals and graphene, so able to receive light in the far IR to mid IR range, all the way to semiconductor or insulating in boron nitride, so being able to absorb UV. And there's a lot of different applications here for communications, as well as solar cells, just from an absorption and propagation standpoint. Now, again, these materials, span the gamut between semiconducting to semi-metal, all the way to insulating. But one of the things I'm also interested in with these materials is looking at this cellular redox potential. So this is basically looking at how cells, the respiration of cells, and I always surprise people when I say, yeah, cells have what's called a band gap. So this is the distance or the energy between the valence electrons held close to the atom, or not close to the atom, but at the surface of the atom, to the conduction band that allows for conduction throughout a crystal. And we actually have quite a few materials that fit that, including graphene. But one of those materials is also this transition metal oxide, manganese dioxide. And so this is another reason why I'm interested in these transition metal oxides, for basically, for bacteria sensing, as well as microbial fuel cells. Now, there's a lot of different ways you can actually make these two-dimensional heterostructure stacks. One is you can mechanically assemble them, like Guy and Novoselov showed. But the issue here is a lot of times these are really isolated to very, very small flakes, and really are not ready to be used. Well, can't be really used commercialized, because it's kind of random in size and scale that you can actually go. Now, the best way, and this is a way that have been traditionally used in the semiconductor world, is through physical epitaxy or chemical vapor deposition. So you can either go atom by atom, like with molecular beam epitaxy, or you can go to chemical vapor deposition, where your molecule, you introduce some gas into the chamber that reacts with your surface and actually forms these heterostructures. And you can in both cases, you can kind of treat this as a way to essentially build like Legos, different materials with different properties, unlocking new properties and physics behind that. Now, jumping over to graphene, because that's what we're using as a scaffold, there's a few different means of actually making this material. One is through exfoliation, which is definitely the cheapest way. Again, taking Scotch tape and peeling it from bulk graphite, and then you slam it down onto a substrate. But again, this is kind of random. You have these random flakes and stuff. So very small area and very poor yield. One means that's actually also pretty cheap is doing a CVD route, where you actually take copper or nickel, and you can synthesize by flowing methane across these metal films to form graphene. But you have to transfer it off this very conductive metallic substrate, and the grain sizes are pretty small. Now, another means is through reduction. You can take graphene oxide, you can spin coat it onto a substrate and dry it, and then you can actually reduce it to form graphene. But again, have pretty poor control over different defects. So all of this is kind of point towards this epitaxial route, which basically uses silicon carbide, which really has been the backbone, I would say, of a lot of advances in power electronics. But you can actually grow graphene using that material, which can now go up to 6-inch wafers, and you can actually get single crystal grain sizes greater than 1 millimeter. Very easy for processing, because you're building on a substrate that's for the most part CMOS compatible. But the issue is cost of silicon carbide, which again, cost is going down dramatically. And you also have this carrier scattering from silicon carbide, because you have this electron phonon coupling that I'll show in the next slide to kind of contend with on the material. So I did my postdoc at the Naval Research Lab, and I focused on this this growth of epitaxial graphene. And so this is the CVD reactor here. This first chamber on the right is actually used for silicon carbide growth, but the chamber on the left is used for the synthesis of graphene from silicon carbide. Here is the chamber here. So it's all graphite here. We have our 4-inch wafer sitting here that rotates in the chamber. Again, it's all made of graphite because we're heating it inductively. So we induce eddy currents into the chamber, and our sample heats up as a result. And we heat it up to around 1580, 1600 C. And the carbon and silicon in silicon carbide have different vapor pressures. So the silicon actually will sublimate out of the material, and graphene will remain, or the carbon will remain behind and restructure itself to form these really nice layers of graphene. Now, this process is also self-limiting because, as you can see, the silicon atoms here are actually much bigger than the carbon atoms of graphene would actually allow. So it's actually self-limiting because, again, the silicon can't get through this graphene lattice. So the actual growth, and especially in silicon phase, is this step flow mediated growth, where you actually get a lot of growth from the A and M planes of the silicon carbide that pretty much propagated along this C plane to form these very nice layers of graphene. Now, as I said before, you have this issue of the silicon carbide phonon scattering, as well as just how graphene grows on silicon carbide. So again, this is step flow mediated. So your silicon is flying out from the step edges in the 1, 1, 2 bar 0 direction. And so you end up with additional layers in that region there, as well as this 6√3 buffer layer that's actually binding the substrate to the this graphene layer here. And as a result, you actually end up with pretty low carrier mobility. As you remember from the previous slide, it said, oh, graphene should be 100,000 centimeters squared per volt second. But because of this electron phonon coupling, our mobility is actually, to be honest with you, pretty on par with what silicon is, which means that, for the most part, it's really, not that big of an improvement, right? So as shown here, we have these dangling bonds of coming from the silicon atoms that are binding this first layer of graphene that's been formed on the surface. Now, one of the things we can actually do is we can actually introduce hydrogen. And what the hydrogen will actually do is go in and actually passivate these bonds. And by passivating these bonds, we actually release this electron phonon coupling as a result. And actually, in this case, the additional growth that we see on the step edges is actually helpful, because now, instead of having 1, 2, and 3 layers of graphene, now we have pretty conformal 2 layers of graphene with a little bit of 3 layers present. And we see a 4 times increase in carrier mobility as a result. And so, we have this very high sheet carrier concentration, 10 to the 13 centimeter square per volt, centimeters per centimeter square, excuse me, and an order of magnitude drop in sheet resistance. So this is a very conductive material and a perfect substrate to fabricate additional materials on top of it. And so this is just showing layer thickness. So again, 1, 2, and 3 layers. This is done by Raman spectroscopy, which basically looks at the phonon vibrational modes. And then from a peak called the 2D peak, we're able to actually see that we have additional layer formed from the promotion of that buffer layer. And so we end up, again, this is the same substrate that we've intercalated, and you see a huge improvement in the carrier mobility as a result. Okay. So with all that said, now we can look at growing materials on top of this really, really great substrate. And so direct synthesis of heterostructures is difficult because you have to lattice match. If you don't lattice match, you'll get this strain-induced defects as shown below in this figure A here. Now, graphene is great because for the most part, it lacks a lot of these dangling bonds and covalent bonds. And so as a result, you can grow materials on top of it that won't actually bind to the graphene. And so this is called this van der Waals epitaxy. The issue is nucleation, which can actually be very challenging, because if you're not actually binding the crystal, to the substrate, then it really needs to kind of figure out the template for which it actually needs to form. And so, I'll show later, ways that we are able to actually create at least a faux template for some of these materials by electrochemistry. Now, I want to start off with this MOS2 epitaxial graphene heterostructure. This is in collaboration with Chris in Korea, where we send our bilayer epitaxial graphene to them, and they actually grow these very wonderful MOS2 nanoflowers on it. And the idea behind this project here was, instead of having a planar MOS2, let's have it structured and be able to enable very high surface area for molecules to actually interact with. And we have a bunch of different samples with different textures to actually explore as a result. And as you can see here, this is sort of the process. We have the synthesis of epitaxial graphene. We synthesize these nanoflowers, and we actually make this four-contact gas sensing device. And what we saw is in the presence of methane, just 5 parts per million, that we have this, very, very quick response in 3 seconds, which is really unprecedented for most sensors of having a response time that quick, especially for a transition metal dichalcogenide sample. And with it being on graphene, we actually saw that it actually has really, really, good signal to noise ratio. The issue is this sensor is really not selective, and it actually shows response to methanol and isopropanol as well, so it's not selective at all, on top of having an extremely long recovery time here. And so the idea was like, okay, well, would we be able to get a better result out of material with the enhanced charge transfer that we typically see in transition metal oxides? So just an overview of the transition metal oxides going towards manganese dioxide. They actually have been historically used as gas sensors. So actually they were the first gas sensor introduced in the 60s. The issue behind these sensors is in order for them to actually have any remote detection capabilities, they have to be heated up. So they really have this relatively low conductivity and responsivity, and you actually have to operate them above 150 C. So I don't know, y'all, but I kind of leery about having a oven sitting on the wall just to detect things like smoke, for instance. But the material is robust and relatively low cost. Whoops. So the question is, can graphene compensate for this by being a carrier source and a conduction path for carriers coming from our transition metal oxide? Now, the difficulty is manganese dioxide has a wide variety of polymorphs and with varying active surface areas, but we're really interested in this layered structure. And so being able to get this delta phase layered structure is actually pretty difficult. As you can see here, if we were to use potassium permanganate, there's actually a lot of different compounds that you can actually get that's not manganese dioxide. But this material is very interesting because it has very large interlayer spacings in between the material that can actually be tuned by putting in different ions in the material. So it actually is, can be seen as a pretty good sensing material that we can actually, tune to whatever a molecule we're actually interested in sensing. Now, something that I didn't mention about graphene is if you heat up graphene with oxygen, your graphene will actually go away. It'll actually, form carbon monoxide and carbon dioxide as it goes, out the chamber. And so we were thinking, like, what is a way we can actually synthesize this material? And so one way is through electrochemistry. And this is actually going off of work from when I was a graduate student at University of South Carolina, where I was trying to actually put hydrogen on graphene to try to change it from being a semi-metal to an insulator. And so, this involves not the physisorption of molecules, but the chemisorption. And so these are actually much stronger bonds in excess of 500 millielectron volts. And typically you would want, these charged atoms or molecules. So these ions and cations are what you actually need in order to actually bond to graphene. And it's already pretty difficult. And unlike with the physisorption that kind of, is random, these are arranged periodically, and they go from these pi bonds to these sigma bonds. So you actually have a change in the lattice. And so, we were interested in putting hydrogen on, but there was a clear oxidation peak here. And so we were like, okay, well, can we actually cycle hydrogen off? And sure enough, you can actually go from pristine graphene, this is again the Raman spectrum, putting hydrogen on, you see, this increase in this D peak or this disorder peak, which is also significant because it actually increases with increasing sp3 content. And then we drove the hydrogen off thinking that, okay, we'll go back to pristine graphene, but it didn't. It actually oxidized. And you can clearly see this through this fluorescence here. And so we were like, okay, well, if we can see the surface with oxygen, we could clearly just put manganese on the surface. And so that's exactly what we did. So we did the cyclic voltammetry, like we did in the previous one, where we cycled the potential and to see the redox potentials in the solution. Here we use manganese acetate as our manganese source. We cycled the potential, and we were actually able to get these potentials at which manganese that goes on at minus 0.4 volts, and hydrogen goes on, or excuse me, oxygen goes on over 2 volts. Okay, so we're able to do this electrochemistry. So we decided to do it in 3 steps, where we seed the surface with oxygen here. Then we flip the potential and we put down our manganese, and then we flip the potential again. Then we cap it off with oxygen. And so the result of that is these thin films. Top surface is actually fibrous, which means that the material actually has even higher surface area than just a simple layered material would. And as a result, we made these 4 contact gas sensors on this electrodeposited manganese dioxide on epitaxial graphene. And we actually had a very surprising result, which was that we saw this very, very fast response and recovery times. Response times of less than 3 seconds and the recovery times of less than 7 seconds. And so we cycled gases on our NO2 and our NH3, and we cycled it on and off. And we're able to see this very, very fast response and recovery time to these gases. Now, the issue here is the responses are both positive, which you would expect in oxidizing and reducing gases to actually have different effects and opposite effects in response to landing on a material. Now, there's a few reasons why we think that might be the case. We think that it's possible that the manganese dioxide is driving the graphene to charge neutrality, which would mean that injection of electrons or holes from these species would cause an increase in current. Now, it's also important to note that you can see that there's a positive trend here for the NO2, and for the NH3 there's a negative trend. So this is something that we're still investigating, and if that is indeed the case, that we're actually having this kind of depletion region of charge neutrality as a result of these materials, or if it's some other structural changes that are happening that's causing this effect. And it's also interesting to note that we exposed this to isopropanol and methanol, similar to the molybdenum disulfide sample, and there was absolutely no response, which is very, very interesting as far as selectivity goes, because graphene would light up immediately if it was exposed to those gases. And so there's 3 effects that we take a look at: the chemical effects, the electronic effects, and the geometrical effects. Now, as I showed before, manganese dioxide has a pretty large interlayer spacing of 7.3 angstroms. We exposed it to ammonia and nitrous oxide, not nitrous oxide, excuse me, NO2. If you look here, the kinetic diameter of those are actually much smaller than the 7.3 interlayer spacing here. Now, methane and then isopropanol is actually a little bit higher than acetone. It's like 4.8 kinetic diameter. Those are actually being screened. And so this is one reason we think that the selectivity side of things is definitely being caused most likely by this screening effect of the interlayer spacing in the material as shown here. Now, as far as the response goes, it could very well be, this electronic effect where we're having two materials, one with majority electrons and one majority holes or lack of electrons, causing this region where we have charge neutrality, where both oxidizing and reducing gases are causing this positive effect in current. And then just kind of a side note, we're actually able to take that electrodeposited manganese dioxide and actually form a different material in forming this manganese diselenide, which is actually a ferromagnetic material, by basically popping our manganese dioxide in a chamber with some selenium and actually doing selenification on the material to actually form this thin film ferromagnetic material. So in summary, basically, we've demonstrated this van der Waals epitaxy on epitaxial graphene by electrodeposition and vapor deposition, as well as the ladder of the solenification, and we've shown this unprecedented gas response times for the heterostructures of less than 6 seconds, due most probably to the enhanced charge transfer with the graphene, basically charge hitting this superhighway. And from the manganese dioxide gas sensor, we've seen this selectivity, possibly due to molecular sieving, as well as this positive response to NH3 and NO2. And this is possibly due to the materials driving each other to this charge neutrality. And I would like to acknowledge NRL and Chris and Clemson. NRL for the graphene, Chris for the MOS2 nanostructures, and Clemson for letting us use their equipment to test these sensors. And I'd like to thank everyone for listening to my talk.
Great. Thank you so much, Kevin. So we have quite a few questions. So I'm going to try to make my way through these, and we'll see how we do. So the first question is from Lucien Weiss. And the question is, if you ramped the temperatures of the sensors, could you distinguish between methanol and isopropanol and make the sensors more selective?
I'm guessing you're talking about the manganese dioxide heterostructures. That is a very good question. And the answer is yes. I mean, that's part of a lot of these sensors is if you do heat them up, you can have selectivity because you're actually breaking the bonds of methanol and isopropanol. So you're definitely right. By heating them up, you can. Now, the manganese dioxide sample is a little tricky because as you saw before, there's a lot of different compounds of manganese dioxide. And we've actually found that if you actually heat up manganese, delta phase manganese oxide past, let's say 150, 200 C, it actually converts to Mn3O4. We think that our manganese dioxide is water stabilized. And if you drive the water off, it immediately converts into this other compound. So yes, I do think we could make these sensors more selective by heating, but probably not with the manganese dioxide.
Great. So our next question is from Jeremias Salam. And basically, so nice talk. The small question is, how are the gas sensors affected by water, i.e. humidity, during operation?
That's a fantastic question. So the results of the sensors that was shown was actually taken, and the room humidity was around 55%. So it was actually pretty decently high in humidity. Now with the manganese dioxide sample, we believe that because we're stabilized by water, that might offer a little bit of protection to humidity. That's actually something that actually the first thing we're planning on testing once we're allowed back in the lab, especially using the system at NRL to be able to characterize these samples, which does have a setup to test different levels of humidity. So that's actually definitely on the forefront of our minds to test and see how water actually affects the sensitivity and selectivity of these sensors. It's a fantastic question.
Great. So the next question is actually from our president, Heidi Leonard, who asks, how does the manganese oxide morphology affect sensing ability?
So that's a very good question. So a lot of researchers have explored, this manganese dioxide and looking at reactivity. And I found that, some polymorphs of manganese dioxide are just not very reactive, especially the bulk counterparts of manganese dioxide aren't very reactive. One of the things that we've noticed, especially from XPS, is that there is a good number of Mn+2, Mn+3, and Mn ions within our structure. And we believe that that in part is helping with the reactivity and therefore affecting the sensing ability of the manganese dioxide. Now, one thing that we do want to try is maybe fabricate or synthesizing some of these other morphologies to see if we actually do see an improvement. But we're really interested in this delta phase, and especially to see if we are getting this molecular sieving effect, because we definitely want to use that just for the selectivity.
Great. So this next question is from Griffin Fields, and the question is, have you found any hysteresis effects in the gas sensors?
I'm guessing hysteresis effects in, are you talking about like turning on and off the gases and actually have a buildup of charge? I'm guessing that's what they mean by hysteresis.
Potentially. There's a delay between the chat and this. So unfortunately, we won't. It's kind of like talking to someone like on the moon.
Oh, of course, definitely. So I'm going to say yes, as you saw that as we turned on and off gases, there was about a 3% shift in conductivity. So yes, there is a slight hysteresis there from turning on and off the gases. Now, if we turned off the gases for an extended period of time, of course, I believe it would return back to its pre-dose level. So yeah, there's about like a 3% hysteresis, I would say, in the sensor.
Great. And then our last question is from Walter Smith. And the question is, why do you get a graphene bilayer on the silicon carbide rather than a monolayer?
So that's a very good question. So before doing hydrogen intercalation, we actually do get a monolayer of graphene. By doing the hydrogen intercalation, that buffer layer that's there gets promoted into another layer to form bilayer graphene. Now, I know you're saying, like, well, why not have hydrogen intercalated monolayer graphene? And the answer is, I've tried. The issue is you actually have to have complete coverage of the buffer layer and then promote that in order to form a quasi-freestanding monolayer that's not under the effects of the silicon carbide. And so what ended up happening is during this buffer layer growth and then promotion, we had these basically pinholes of incomplete growth of the buffer layer. And as a result, the mobility, instead of it being 4,000 or 5,000 centimeters squared per volt second, the highest we were able to get is around 2,000, 2,500, because now you're introducing defects and scattering sites into the layer.
Great. All right. So with that, I want to thank you again for a fantastic talk. Thank you so much, Kevin. For everyone else, please feel free to tune in next week. We have Dr. Jijan Su from Princeton University, who's going to be discussing ultra-sensitive Ebola virus antigen detection via a nano antenna array biosensing platform. But for today, thank you so much again, Kevin, and we'll see everyone else hopefully next week.
Thank you.